In this question, we want to know if f is increasing on the interval from -5 to 3. When a function is increasing, it's referring to the y, and this interval is the x. So I want to look at my x scale to determine which interval I'm talking about. This interval will start at -5. Here's an x of -5 and end at an x of 3. So I'm going to highlight the interval that we're talking about. So I want to determine if the y values in this region of the graph are increasing. So I'm going to trace the y along this interval, starting at x equals -5. I always want to trace going from smallest to largest. And that goes from left to right. And as I'm tracing this portion of the graph, I know the y values are getting larger and increasing. So along this section of the graph, the y values are increasing. And then I get to this peak, and now the y values are getting smaller or decreasing. Along this section, the y values are increasing. So there are a few sections along this interval where the y is increasing, but f is not increasing on the whole interval. So we're going to answer this question no. The function f is not increasing on the interval from -5 to 3. In this question, we want to list the values of x for which f has a local maximum, and what are these local maxima, if they exist. So I'm looking at the graph and trying to determine if I have any local maximum. And what I'm looking for are changes in the graphs increasing and decreasing. So let's take a moment to look at this function overall and decide where the function is increasing and decreasing. So I'm going to trace the graph going from left to right. And as I trace along this section, I notice that the y values are decreasing. So let me label this section of the graph is decreasing. At this point, the y values are now increasing. And then it switches again to decreasing. And then it switches again to increasing. And then it switches one more time to decreasing. When I'm looking for a local maximum, maximum meaning highest or largest, I'm looking for the places when the graph changes from increasing to decreasing. If it changes from increasing to decreasing, it creates a peak, which is a maximum, a local maximum. And that's happening in a few places along this graph. Right here, we see a change from increasing to decreasing, which creates a local maximum. And here's another point where the graph changes from increasing to decreasing, creating that little peak. Now we notice that these two peaks are not the highest y values of the graph. We notice that all of these y values are larger. Even though they're larger, the word local is allowing us to narrow our focus to a localized area. So if we were to focus on only this portion of the graph, we notice that we do have a maximum in that localized region, and the same goes with this region here. in this localized region, we do have a maximum value. And so that's why we preface the word maximum with local. It may not be the maximum of the whole graph, but in a localized area, it's the maximum. So let's take note of the ordered pairs where we have these local maximum. This first ordered pair is -1, 1, and the second ordered pair is 3, 1. So our function has local maximum at x equals -1 and 3, and the local maximum refers to the y, the actual largest y value in that localized area, and that is 1 for both ordered pairs. So we have two localized maximum at x equals -1 and 3, and the local maxima is 1. On this question, we want to find the average rate of change for the function between the given values. The function we're working with is f of x equals x squared plus 3x. And we want to find the average rate of change from x equals 2 to x equals 7. Now the formula for average rate of change is very similar to the slope formula for a line. The average rate of change formula is f of b minus f of a over b minus a. The slope formula is y2 minus y1 over x2 minus x1. If you look at the average rate of change formula, f of b and f of a are two y values, and we're subtracting them. And then we have their associated x values in the denominator that we're subtracting. So this is very similar to the slope formula. And the main difference is that with the slope formula, we're going to be using 2 points on a line. And with the average rate of change, our 2 points are on this function here, which doesn't necessarily have to be a line. In our example, we're going to let A be 2 and B be 7. And we need to calculate f of b and f of a in order to be able to apply this average rate of change formula. So f of b is f of 7. So we'll substitute a 7 into our function f of x to get 7 squared plus 3 times 7. 7 squared is 49, 3 times 7 is 21, and 49 plus 21 would be 70. And we'll find f of a. F of a is f of 2. That's 2 squared plus 3 times 2. 2 squared is 4, 3 times 2 is 6, and 4 plus 6 is 10. Now we'll apply this average rate of change formula. F of b is 70, f of a is 10, so in the numerator we have 70 minus 10. In the denominator we have 7 minus 2, that's b minus a. So simplifying the numerator, 70 minus 10 is 60, 7 minus 2 is 5, and 5 divided into 60 would give me 12. So the average rate of change for our function f of x equals x squared plus 3x from 2 to 7 is 12. In this question, we want to do the following for the function f of x equals 3x plus 2. In part A, we express the slope of the secant line in terms of x and h. In part B, find the slope of the secant line for h equals 0.5, 0.1, 0.01 at x equals 1. What value does the slope of the secant line approach as h approaches 0? Find the equation of the secant line at x equals 1 with h equals 0.01, and graph f and the secant line found in part C on the same viewing window. So let's start with expressing the slope of the secant line in terms of x and h. I'm going to give a little background. There is a formula for slope of the secant line, but I'm going to describe where it comes from. So we'll start with a curve. So we have some curve on our graph, and the secant line is going to be a line that crosses through 2 points on our curve. So I'm going to let x be the first point, and then the second point will be a little bit further down. And we'll say that little bit further down is the amount of h. We would take 2 points on that curve that are associated with that x and h and connect them with a straight line. That straight line is the secant line. So this is the secant line. Now the y values that go with those points would be f of x for this first one here, and f of x plus h for the second one. Now we're interested in finding the slope of that secant line. We have a formula for calculating slope of a line that's y2 minus y1 over x2 minus x1. So we'll use this f of x plus h as our y2 and f of x as our y1. That will give us f of x plus h minus f of x all over, and we're going to use x plus h as our x2 and x as our x1. We have x plus h minus x, and we can simplify that denominator. I'm copying down the numerator, and the denominator, the x's would cancel, leaving me with h. So this gives us a formula for calculating the slope of the secant line. So we label that with m for slope with a subscript of SEC for secant line. So our formula for slope of the secant line is f of x plus h minus f of x over h. That's a general formula for the slope of the secant line. We want to find the slope of the secant line for our function f of x equals 3x plus 2. So I'll start off by finding f of x plus h. Everywhere I see an x, I'm going to change it to x plus h. So that becomes 3 times x plus h plus 2. And then I want to subtract f of x. Our function f of x is 3x plus 2, and notice I put parentheses around that function. And that's to make sure that this minus applies to the whole function and not just the first term. In the denominator, we have h. So I'm going to use the distributive property on this 3 and the distributive property on this negative. That will give me 3x plus 3h plus 2 minus 3x minus 2 over h. 3x minus 3x is 0. 2x minus 2, that's a 2 minus 2 is 0. And I'm left with 3h over h. The h's cancel, and I have 3. So the slope of the secant line is 3. Now the reason why the x and the y canceled out in our expression is because our function is a linear function. F of x equals 3x plus 2. If we were to use another function that wasn't a linear function, the slope of our secant line would have the variables x and h in it. So this is the answer for part A. The slope of our secant line in terms of x and h is 3. In part B, we're asked to find the slope of the secant line for h equal 0.5, 0.1, 0.01 at x equals 1. The slope of my secant line doesn't have any variables in it, so I don't have anything to substitute into. But if my function was something other than a linear function, I would have x and h within this slope of the secant line, and I would substitute the different values of h as well as the value of x to answer part B. For this example, part B will have the answer of 3 for every value of h. The slope of the secant line is 3 for all of these values of h and x. So it's 3 and 3 and 3 for all three of those answers. In part C, we want to find the equation of the secant line. And to find the equation of the secant line, you need the slope and a point on the line. Now we've already found the slope. That slope is 3. This is the slope of the secant line. And we have x equals 1. We need to have the y value at that point. So remember, my function is f of x equals 3x plus 2. F of 1 is 3 times 1 plus 2. That's 3 plus 2, which is 5. So this is the ordered pair that I'll use to find the equation of the secant line. The formula is y minus y1 equals m times x minus x1. We call this point slope form. And I'll substitute the slope as well as my ordered pair into this formula. That gives y minus 5 equals 3 times x minus 1. I'll use the distributive property on 3 to get 3x minus 3 and add 5, and this gives y equals 3x plus 2. Y equals 3x plus 2 is the equation of the secant line. I'm going to zoom out a little bit so we can see our question again. I want to make sure we answer all the parts. And I just noticed that I missed this part of the question right here. What value does the slope of the secant approach as h approaches 0? All of the slopes of our secant lines were 3, and so the slope of the secant line approaches 3 as h approaches 0. Finally, part D, we want to graph f and the secant line in the same window. So I have the graphing calculator right here. And our original function was y equals 3x plus 2. And the slope excuse me, not slope, equation of the secant line is also 3x plus 2. And to graph them in the same viewing window, they are the same line. So this is a little unusual, but because the function is a linear function, the secant line is the same as the original function. And so we've answered all of the parts on this example. On this question, we want to match the graph with the given functions. So our choices are the square function, the square root function, reciprocal function, cube root function, absolute value function, identity function, cube function, or constant function. So I know immediately which function this goes with, but I'm going to go through each one of these functions and give you a sketch of the graph. The square function refers to f of x equals x squared and has a graph of a parabola. The square root function is f of x equals square root x, and this graph is half of a sideways parabola. So it looks something like this, the top half of a sideways parabola. The reciprocal function is referring to 1 over x, and it has a graph that looks something like this. The cube root function is f of x equals cube root of x, and is a little bit long horizontally. It goes through the origin, kind of has a little squiggle in the middle. The absolute value function is referring to f of x equals absolute value of x, and this graph has a V-shaped graph. The identity function is f of x equals x, and this is a linear function going through the origin. Cube function is f of x equals x cubed. I'll go ahead and draw this over here. The cube function is going to look very similar to the cube root function, except that this function is much longer vertically than it is horizontally in the cube root. The constant function is f of x equals b, where b is a constant. And the graph of a constant is a horizontal line at the value of b. So the function that this matches is the square root function. And I'll take a moment to go into a little bit of detail about this square root function. F of x equals square root of x. We can find the graph of this function, if you don't have it memorized, by plotting points. And when I plot points, I'm going to choose some values that are easy to find the square root of. So I'm going to start with 0. I'm not choosing any negative values because the square root of a negative gives you imaginary numbers. So I'm starting with 0 and 1, and then I'm going to jump to 4 because 4 is easy to take the square root of. And then I'll choose 9 as well. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. And I'll plot these ordered pairs on a coordinate plane. I have 0, 0, 1, 1, 4, 2, and 9 and 3. And hopefully you see why we chose this function as the one to match this graph. We have our square root graph here.